calculational problems.
Well, at least with the isentropic, as you compress it, it's heating up, and so the gas is going to push more against the work you're doing. So if you do more work, then you compress it down.
Outstanding answer, right? So as you go through a compression, if you're compressing a gas, as you compress the gas, the temperature rises, which means each stage of the compressor has to compress. Remember, we just said that it's the volumetric flow that determines how much work you have to do. So as the temperature rises, the volume that you have to compress is increasing and increasing. And so it does more and more work as it does the compression. So why is it that there are essentially no isothermal compressors used in industry?
Real gases don't compress without increasing temperature.
Okay. So, but real gases will increase their temperature too. So over the pressure ratios that most compressors operate, you could use an ideal gas expression for the gas and you'd be fine. So that's a good thought. So real gases, so we'll take a tangential question. Is real gas going to be typically harder or easier to compress than an ideal gas?
Depends on the gas.
So almost always easier. So it turns out all gases have attractions to one another, right? Gas molecules. So ideal gases don't have any. All real gases have some attraction to one another. That's the, remember that in the ideal gas equations that have the correction that they put in there is always a negative correction. So real gases are almost always easier to compress. Sometimes immeasurably easier, but easier than ideal gases. So back to.
So I think in real processes, you want the compression to happen extremely quickly, and so you can't really have isothermal because it needs to be timed for heat to do that.
Right, another good engineering intuition. So the velocity of the gases through this compressor is really fast, and there's just not enough time to cool anything down as it goes through the compressor. Now, sometimes they do, and this is not uncommon. So they'll have what they call a multi-stage compressor, and this is a way that you can save a substantial amount of energy if you're doing something that's compressing a lot of gas. That is, they'll do partial compression, and then they'll bring the gas out and go through a heat exchanger, and then they compress it a little bit more, and then they go through a heat exchanger and they compress it a little bit more. And they do 3, 4, 5 is pretty common stages. 8 sometimes would be a remarkable number of stages in order to save the energy on compression. So you can save quite a bit of energy. So a typical compression process, you can save 25% of the energy of the compressor. The compressor is usually the biggest part of the energy consumption by staging it that way. So that's trying to get closer to isothermal. It's a bunch of little steps. It's not really flat, but it's in the limit of an infinite number of stages, you have an isothermal compressor. You see a question?
Well, I was going to ask if we could go back to the slide with all the efficiencies on it. I was going to ask, so the last question we were supposed to find the rate of consumption of fuel. In my thought process, I was wondering if you could point out what I did wrong. So W dot, I said was the horsepower.
That's right.
And then
This is the
age of combustion, that's I threw in the BTU per gallon and found
right.
and the efficiency, and the M dot I was solving for was what I thought was the gas being consumed.
Yeah, that is right. That should be what you got. So you should have gotten gasoline consumption in gallons per second or something like that. So why do you know you did something wrong?
Well, earlier Connor asked if the M dot was gas, and you said it was air, but you must.
Oh,
it was
I'm sorry. This M dot.
case.
I'm sorry. This M dot is gasoline. Sorry for that. I thought you meant. I guess I didn't put the M dot up. This M dot is the air pressure there. Sorry for the confusion. All right. So everybody comfortable with all of that? So important concepts are here are for turbo machinery in general, compressors and turbines, the most common for gases. It's really the volumetric flow rate that you did think about. So this would be a great conceptual question on an exam. Is if I were to compare argon and helium that have a molecular weight that's different by about a factor of 10. If I put argon and helium through the same turbine, which one is going to generate the most work, assuming that the pressure ratio is the same and assuming that the volumetric flow rates are the same, which one produces the most work? They're the same, right? Even but which one has the highest mass flow rate? Argon is 10 times higher mass flow rate, but produces the same amount of work, all right? Then if we study hydroturbines, we'll come back to the mercury versus water turbines. All right, so Greg was here yesterday. I hope everybody, there's a great opportunity for you to make some easy money by applying for that scholarship if you want to, if you go through that. So first, some conceptual things. Greg mentioned this the other day, but he didn't show you the numbers. So most of you are probably aware that in the United States we have closed, we are building some nuclear power plants, but we've closed more than we're building. We're shutting them down faster than we're building them, actually. And and coal is also in the decline, and most people blame global warming. Maybe you think that global warming is why coal is being decreased, and I'm not sure anybody knows why we're closing nuclear power plants. But what I want to point out to you is that in the future that could very well be the case. So global warming may be a major reason that we shy away from coal in the future. But currently it's not. If there were no global warming and nobody were worried about it, we still would be closing coal-fired power plants. And this slide shows you what both coal and nuclear would be closed down. So the reason they're closing down right now is just 100% economic business decision. It's not because of any bias toward coal or anything else. This shows the this is for residual fuel oil that some people still use for power generation. But this is the cost this is the dollars per million BTU for a variety of different fuels. For natural gas and coal, really, and oil, but ignore the oil right now. And natural gas used to be in the dollars per BTU. They used to be more costly than coal, but the natural gas power plant is cheaper to build. And so you would say, well, the power plant is cheaper, but the gas is more expensive, and most people opted for coal because over the long run, the coal was cheaper. Coal comes in several varieties. We'll talk about that next week, actually. But the kind of coal that we burn in the western United States is typified by Powder River Basin coal, which comes out of the state of Wyoming. Wyoming, by the way, supplies half of the coal that we consume in all of the United States. Half of it comes from the state of Wyoming. So, and that's really cheap coal. It's easy to mine. At the mine, it costs about $3, sometimes a little less than $3 per ton. So think about that for a minute. A ton of dirt would cost significantly more than $3, right? So a ton of anything, just the idea that you can buy a ton of anything for $3 is a pretty astoundingly low price. And of course, if you buy it 100 pounds at a time, it doesn't cost $3 a ton. But when you buy it many tens of thousands of tons at a time, at the mine, it costs $3 a ton. By the time it gets to the power plant, you have to pay to rail it to the power plant, and it's up to $19 or $20 a ton. So that's really, really cheap coal, and it's still the cheapest source of energy that we have. You can see that one here. But the coals that we mine in the eastern United States, the Central Appalachian coals, are this yellow line, and they're considerably more expensive. So the Wyoming coals are typically open pit mine. There maybe be 30 to 70 feet of dirt you have to scrape off the top, and then you just load up coal in the biggest buckets that they can build and put on things, and they're big. They have one big scoop that will just scoop up 25 tons of coal at a time, and they dump it in the back of one truck that can carry 25 tons of coal at a time. Or sometimes they just put a drag line that just transports it right out of there. One person picks up 25 tons of coal and does that every 3 or 4 minutes and just pulling it out of the mine. So that's really cheap to mine that way. By contrast, it's the underground mines, which we have in Utah and in most of the eastern United States. So now you have to dig way underground and have a relatively thin coal seam by comparison. And you have this, you have to prop up the mountain on top of you as you're digging through this coal seam. and you're dealing with a bunch of labor unions that increase costs significantly. So that's way more expensive coal to mine, and you can see where, that's why it's up here in terms of, actually has more energy per unit mass than the coal that we mine from Wyoming, but it's way more expensive to mine. And then the important thing is that recently, and these are all recent prices, natural gas is as cheap, or in some cases cheaper, than at least the eastern coals. And so when you're in that condition, so this is less polluting, the power plant is cheaper and faster to build, it responds more rapidly to changes on the grid. There's actually no reason other than cost. Cost used to be the only reason you used to burn coal. This used to be 10 times higher, so this was up to here. But now it's down here so low that people say, why would anybody build a coal plant, especially a coal plant that burns eastern coal? And that's the reason the coal mines are being shut down. Nuclear plants cost even more than coal, so the fuel for the nuclear plant is close to zero cost, but the levelized cost is even higher than a coal-fired power plant. And so nuclear is the reason that nuclear plants are so hard to get people excited about right now is that you can generate the same amount of energy, you can do it at a much lower cost, and with a lot simpler and cheaper plant, a lot less capital, tying up a lot less capital if you do it with natural gas. Now, looking to the future, that could all change, and things like global warming and other things can change. So Greg talked about, and I'll review a few parts of this, he talked about how you produce natural gas in some of the properties. He didn't talk too much about how you use natural gas, so I wanted to talk about that. So natural gas is used primarily in two different ways. What we call a simple cycle turbine, or some people just call this a combustion turbine. And this is a typical example of one for power generation. So they have a big air inlet on the front, and they don't show it, so there's a bunch of filters here. They want to get the air as dry and as clean as it can be, get all the particles out of it. So right up front, there's a bunch of big air filters and some dryers to dry it out a little bit. Then they can pull the air through the compressor, and just like we talked about so far, the compressor comes through here, and then they have these, they call them combustion cans all the way around here. We'll see an actual picture of them in just a minute. And so the air at this point is compressed. It goes through these combustion cans, and it burns, and then it goes through the turbine, and it expands, it comes out the back end of the turbine. But it leaves the turbine still at a pretty high temperature. The pressure has already dropped to atmospheric pressure, so you can't expand it anymore to cool it down, but the temperature is still pretty high. And so what would be the obvious thing to do to get more energy out of the system?
Heat exchange, the exhaust.
All right, so if I set up a heat exchanger back here, and I use this high temperature gas to boil water, for example, to make steam, and then drive a steam turbine with that steam, then I have, so first of all, what's this cycle called? Do you remember the names of the cycles? Brayton cycle. This is called the Brayton cycle, the gas turbine cycle, the compression. And this one we haven't talked about yet, but the steam cycle is called the Rankine cycle. That I think might be the only one that you studied in thermodynamics class. Does that sound familiar with the Rankine steam cycle? All right, so we come out of the back end of the gas turbine here, and then we build another cycle, Rankine cycle, where we heat up steam, superheat steam actually. Steam goes through a steam turbine and it recirculates here. We use the high temperature from the exhaust of the gas here to drive the steam turbine. And then now the air that came through the combustor is back down to room temperature, and we've extracted just about all the energy we can from it. That's called a combined cycle plant. Combined cycle meaning a Brayton cycle plus a Rankine cycle. Right? So, and this is what the front end of that. This is GE's. These are people to give you an idea of scale. This is GE's frame H-class gas turbine. These are the little combustion cans, they call them, where the combustion happens. This is the compressor, and this is the turbine expansion system that's on the back end. So let's look at some specifications. So these are really, you can get warranties for these, but it's the best turbine operated under ideal conditions. I'll give you an idea of what more typical performance are. So this is for the GE, they call them H-frame turbines. That's a picture of the turbine up there. This is a picture of one being shipped. And so for the 9HA, point 0 and point 2, for the simple cycle, SC, simple cycle net efficiency is about 42%. So a more typical value for a simple cycle net efficiency is probably in the 35% range. But these ones are, so if you're operating them as a simple cycle system, you get about a 42% efficiency from this turbine. If you do, let's see, look at some of these others. The turn down ratio, this is an important number for you, everybody to think about. So what is the ratio between the maximum amount of power we can produce and the minimum amount of power we can produce that's not zero? So we're still operating and still producing power. We haven't actually shut it down, but it can operate reliably and sustainably. And you get about a factor of 3 on the turn down ratio for the simple cycle plant. And the startup time for this simple cycle plant is, it takes about 23 minutes to start it up from a cold start. But if it's in a peaking mode where you're just following the load with it, it takes about 12 minutes to change the load. So you can go from 30% to 100% output if it's running that way in about 12 minutes. That's quite fast and a really important parameter.
On this kind of turbine, does that cause wear on the turbine to change it?
So that's why it's 12 minutes. So if you did it any faster than that, it would compromise the turbine. But as long as you move it as fast, no faster than they say you can move it through cycles, then it doesn't. So it doesn't cause wear per se. It thermally stresses the turbine blades, and they actually keep track of how many times you've thermally stressed them, and that's what determines the turbine lifetime. Is when you've gone through so many cycles outside of the parameters, then you have to retire the turbine. So the combined cycle plant, this is combined cycle specifications for a dual plant where they would put 2 of these side by side, or a single plant. So the efficiency goes from 42% up to 62, 63%. So a big increase in efficiency by putting the extra cycle on the back end. And more realistically, these would be in the high 50s, so that plants operate pretty routinely in the high 50s. Those are in the mid 30s up there, so almost a factor of 2 increase in the efficiency. The plant turn down ratio from minimum load is not quite as good for this combined cycle plant. You can't turn it down quite as much. But if you do the 2 times plant, then you can turn one of them off, and you get down to a turn down ratio of about 5, which is very good. That's about as high as anything is going to get. And the startup time, this is on here somewhere, and I might have forgotten to underline it. There it is. Startup time is less than 30 minutes if it's hot already. All right. If it's not hot, it takes hours to start these up. Many hours to get everything up to temperature from a cold start. So, but if everything's running and hot, you can change load over about 30 minutes. So that's the way that we use these, the kind of the technologies. So a bunch of this is what Greg talked about last time. This is probably significant to see that natural gas, it's not as dramatically obvious as it is really dramatic, but it's becoming a larger and larger fraction of our total fuel use, and especially natural gas production. So this is conventional natural gas production, and conventional is actually a small fraction of what we actually produce now. So this is the shale gas and tight gas that we talked about last time, and they're dominating production and will for the foreseeable future.
Has that prediction changed since oil fell, price of oil fell?
So the most recent numbers are the prediction. Probably, I don't know. I don't think it has. I actually have I had the more recent data in the first day of class that we went through, and it's on there. I don't think it's changed appreciably. But you can see how the production has increased. So this was basically so you might have, Greg didn't dwell on it, but he mentioned that people have been fracking for generations. They've been fracking natural gas flows forever. But they haven't haven't been fracking them as efficiently, and in particular in shale, to produce oil, liquid oils like they have in the past. So there's some kind of new fracking kind of technology where they got some slides on what fracking is here, and we'll talk about it in just a minute, but that's what's mainly responsible for this big surge in natural gas. And really what's responsible for it is that people are going into the shale deposits, fracking the shale deposits. Mostly they want to get the natural gas liquids out, which are the propane, butane, and heavier materials in the natural gas. Those are the valuable things. That's where they make all their money. Most of these places are at best breaking even, or probably losing money on the natural gas itself. But natural gas liquids have been valuable. Not as valuable now as they used to be, and just to give an idea of how valuable they used to be. So I think today oil is $44 a barrel or something like that. It was over $100 a barrel just a year and a half ago. And so that difference from 44 to 100 would all have been profit when they were doing this for. So that's why there was such a big surge. But people are still operating. We haven't appreciably decreased, even in the most recent data. The amount of natural gas we're producing hasn't appreciably decreased. The profits have decreased dramatically.
So, you talked about how gas wells decay very quickly. Is there like a peak gas, or are we gonna ever use it?
So that's a good question. So now that they're extracting all this gas out of shale, most people think there was just an announcement in the news. I don't know if I read the news all the time, but I did when I was in undergraduate school. But they just announced a major new shale find in West Texas that is like that increases our total reserves in the United States by 15%. Huge new shale play. And one company announced that they bought the property. You never know if it's to their advantage to get a bunch of people who are really excited and buy stock. Sometimes these things are a little overblown when they get announced, but nevertheless, we're finding a lot of shale, and there's every reason to believe there's a huge amount left. So clearly all fossil fuels have a finite life, but with respect to coal and natural gas and oil, we will probably stop using them for reasons that other than running out of the resource. So, petroleum, that may be true now with petroleum, that we're doing fracking as well, but certainly wasn't the past. There was genuine concern we were going to run out of petroleum before we found another technology. So this is in the Utica region. This is where the Utica region is, where they're producing natural gas. This is the region where if you saw you can go on YouTube and see people lighting their water, tap water, and they put a match next to it and it catches on fire. So the EPA has never been able to reproduce those results. But they're still widely cited. So, this is the Marcellus region. Similar kind of big surge in natural gas production. Greg went through most of this. I did get the most recent data I could find, and so you can see natural gas production has leveled off, but it's not declining like you would expect it might. It might start to decline, and arguably it is just barely starting to decline here. It's hard to know, but it's not. So far, the low costs have not driven a bunch of people out of business, although money is definitely tight. So we talked about the composition, so mostly methane, has a bunch of other things in it. What Greg didn't talk about too much is, so there are pipeline specifications. This is natural gas as it comes out of the ground. What he spent most of his previous career, just recently, doing was turning this into this, which is get the CO2 content down to less than 2% typically, get rid of the inerts like nitrogen, and there should be virtually no oxygen, no sulfur compounds, and mostly they extract almost all of this in, the ethane is debatable whether they put that into natural gas or not, but everything else is way more valuable as a liquid transportation fuel than it is as a gas fuel. They don't want it to condense anyway. So there is also liquefied natural gas, and there's a, well, So this is just asking to be confused. So there's LNG, liquefied natural gas, and NGL, natural gas liquids. So they're both liquids and they both come from natural gas, but this is methane that's been liquefied so that you can ship it long distances. This is things that are heavier than ethane, either ethane and everything heavier or everything heavier than ethane, which you extract from natural gas and eventually ends up in somebody's gas tank somewhere. So these are C2 or 3 plus, and this is just regular natural gas, not too regular. So that the specifications for LNG are, you can see them here, but they're richer in methane than the specifications for natural gas are. And in particular, they're much lower. I don't have it on there. Probably have it on here. Oh, these are pounds of pollutants. So they can tolerate, they'll tolerate up to 2% CO2 in natural gas in pipelines. But for liquefied natural gas, the CO2 content specification is 50 parts per million. And it turns out CO2 is really difficult to remove. That's the most difficult step of processing natural gas, is removing the CO2, because it forms an CO2 and ethane form an azeotrope, and it's hard to get the CO2 out and leave the ethane in with most processes. So we went through the pollutants.
Natural gas to get the price down, what's going to be the big factor? Is it going to be a decrease in our reserves, or is it going to be an increase in the demand? What's going to bring the natural gas price up?
So people who answer that question mostly sit in tall office buildings in big cities and get paid huge amounts of money. And the honest answer is they don't know the answer to it any better than you and I do. But here are some considerations. So we are shifting quite significantly toward natural gas for power production. It's a large consumption of natural gas. So, and because the cost of oil is low, the profit margins for natural gas are really low. So it would be really easy to believe, a very logical conclusion of all of this is that several natural gas suppliers are going to go out of business because they can't continue. Many of them have been operating at a loss for a while, so companies operate at a loss fairly frequently. It's just that it's many times cheaper to operate at a loss than it is to actually close down. Airlines do this all the time. They go for a year without making a profit, and then the next year they make an unbelievable profit. And so over time they do all right, but in any given instant, companies may be operating at a loss. And several natural gas companies right now are probably operating at a loss. So if energy prices stay, we call it low, but remember the slide we saw on the first day, it's really not, they're not that low compared to the historical averages. They're actually still higher than the historical average. They're just low compared to the relatively recent history. So if they stay where they are, and there's a lot of reasons to believe that they will, then probably several companies will go out of business, and the demand is increasing, but the supply will decrease, and that will drive the price up. So, but people have been predicting that for a long time. So one sure way to embarrass yourself is to try to predict anything about what's going to happen in any aspect of energy more than a year ahead of time. So these are where the natural gas shale plays are, where we're getting most of our natural gas right now. This new Alpine one is right in here in this spot. But you can see there's natural gas more in a lot of parts of the United States. Talk about how you produce it. This might be interesting to you. So this is actually in Wyoming near Pinedale, but in the Uinta Basin, and I have that slide in here as well. This is just a map of natural gas wells, and this is 1 mile by 1 mile. And so look at the number of wells there is in that. So you could relatively easily walk around that, look at the density of wells that they have in natural gas plays. So there's lots and lots of natural gas plays. And the Uinta Basin looks even more dense than that. Is even more dense than that in terms of how many natural gas wells have been drilled. All right, fracking. So this,
Wouldn't it be more efficient to frack those wells instead of put them
that close to each other?
So they do still frack them. We'll just talk to fracking is like,
I guess in the
directional
frac,
drilling kind of
yeah,
thing.
horizontal drill.
So the horizontal drilling, they're doing that more and more, and that's increasing fairly significantly, but it is still expensive, so, the directional drilling costs quite a bit more than others, but in shale plays in particular, these are traditional natural gas deposits, but shale plays, they almost always frack it, and we'll talk about it, so let's see what fracking is.
So with like a normal oil, rig or whatever, it has like the arm that pumps up and down. Is that the same for like a natural gas well?
No, so these are gases, so they'll usually come out of the ground, you usually try to control the pressure down, so you almost never have to pump them out. You pump them across the ground, you compress it, pump it in pipelines on the ground, but getting it out of the ground is not one of the problems. Because you think about it, the pressure in the reservoir is basically the pressure of the water would be at that depth, and natural gas wells are approximately the same depth as oil wells, about a mile underground. And so there's a lot of pressure, and the weight of the gas in the pipe is small, right? So once you get in there and it starts producing natural gas, it's not hard to get back out. So fracking. So first let's talk about what fracking is. So as always, these are never to scale. So this is a mile, and this is 2 feet this way. So you come and so you drill down here, and they don't turn this rapidly either. So they come down in kind of a long, gentle sweep. But eventually you can get these wells to be horizontal. And this is shale, for example, some formation that you're trying to produce. And you drill through here, and initially you just drill through here and until you're at the end of the formation, or until you're to the point where you're going to extract the rest of it from another well and from another direction. And then, once you've completed the well, you send a little device down here that actually explodes and perforates the pipe that you put in here, and then you pressurize. You do this one at a time, so not all of them at the same time. And then you sand. Traditionally, it's been water with sand in it. The sand is coated with what the thing they put in it is called proppant, which is usually sand that's been coated with hydrocarbons or other things to make it easier to pump, because sand has sharp edges and it makes it abrasive when you pump it through. If you make it more spherical and round, then it's a lot easier to pump. And to help with both its strength and its resistance to the materials that's going to encounter in here. So you pump this slurry of sand and water into this thing at very high pressure, and it fractures the formation. So think of this as sandstone with a bunch of gas trapped in it and oil, and you fracture the formation. And then they've been doing this for a long time, but in the past what they've done is they just fracture it and then you pull the gas out. And if all you're doing is pulling gas out, that works fairly effectively. But if you're trying to get the liquids out as well, as soon as you let the pressure off of it, all those rocks kind of settle back into where they were before, and they seal themselves up again, and you can't get the liquids out very effectively. So the new thing in fracking is these proppants that you put into the liquid, and they get into wedges between all of these rocks, and you pull the liquid out, but the little sand particles stay there, and so now the rocks can't collapse back into their original formation, and so now you have this big fractured formation, and you can pull gas and the liquids, so that at the temperatures that exist down here, these are all usually supercritical or liquid or gas-like substances, but you're pulling them out of here at a relatively high temperature and producing the natural gas. So we used to recover maybe 15, at best 20% of the hydrocarbons from a formation like this. Actually, if it was tight sandstone like shale is, probably more like 3 to 5%. And now people are getting recoveries up into the 60% range of these same materials. So the materials that used to be wells that people drilled a long time ago and decided were dry are now potentially useful again for extracting hydrocarbons, and you can much more effectively extract these things. So once you finish this one and you seal this off, and you do the same thing, and you just keep marching back here until the whole formation is fractured and you produce the whole formation. So the very most recent thing that people are doing is using carbon dioxide instead of water with the proppants to do the same thing. And carbon carbon dioxide has the advantage of the hydrocarbons, almost all of them will absorb carbon dioxide. So the carbon dioxide dissolves in the oil and makes it less viscous, so it flows out of the formation easier than if you use water to do the fracking. So I don't know if everybody's going to start doing that or not, but a number of people have done that successfully in the very
Yeah,
recent
so
past.
you're saying you use carbon dioxide instead, wouldn't it? Is that gonna be just a lot different, because like carbon dioxide's, it's a gas versus like a liquid? How does that work?
So the pressure here is, the pressure of the formation is typically 200 to 400 bar. And then when they're doing the fracturing, you're up to 600, maybe 700 bar.
So it's condensed.
Yeah, so it's really dense. So at those pressures, depending on the temperature of the formation, at those pressures, CO2 will actually be more dense than, it's still technically a gas or a supercritical fluid, but it's more dense than water. So.
Will that also help you save on separation costs, so getting the water out of the...
Yeah, and so when you pull it back out again, the CO2, well, it saves and not saves. So the CO2, yeah, so people are increasingly going to be required to make sure they recover all of the CO2. They want to anyway, because the CO2 is pretty expensive. To buy CO2 for an operation like this typically costs $80 a ton for CO2. I'll put that in perspective. Remember, coal and oil was $3 a ton, right? So you don't want to just vent it into the atmosphere, but because of climate change issues, they don't want to vent it either. So that's the fracking operation. Greg talks a lot about the natural gas processing. I just want to step through a traditional processing thing one time. So first you remove the water and the condensates, then you remove the acid gases, which include CO2 and any kind of sulfur and other kinds of processes. You actually use, the sulfur process is not, if you have sulfur, typically in the form of hydrogen sulfide and natural gas, you remove it by something called the Klaus process, not the amine process. Amine treating removes CO2. Then you dry it back out again, remove whatever mercury there is. This just goes through some typically aluminum-based mole sieves, reactivating carbon. Try to get rid of the nitrogen. This is where you start going through a cryogenic process. And then you recover the natural gas liquid. So this is where you cool this way down to maybe a negative 120 to 140 C. And condense all of the natural gas liquids you can. You sell those, the liquids come out down here. This is where the natural gas goes. The natural gas goes out to the pipeline, and then the liquids you sell to a power plant or to a refinery, and they refine them, and they go through that. So that's classical chemical engineering kind of a process. So you did some homework about the Crittenden therm, and I don't think we talked about the Crittenden bar, but this is a little counterintuitive. So for a pure substance, this doesn't ever happen. So the critical point on a pure substance is always at the maximum temperature and pressure at which you can get two phases. So there's no part of this curve on that side. There's no part of this curve above that point. It kind of comes up and goes back like this. So, but for mixtures of substances, you can and almost always do in the case of natural gas get to a point where you can have a gas and you can decrease the pressure of the gas and form a liquid. As long as the temperature stays constant. So usually if you decrease the pressure, you think you're going to create more gas. If you have a liquid, you would vaporize it. But in this case, as you decrease the pressure, it might form a liquid, and then you continue decreasing the pressure, and then it goes back to all gas again. And so that's kind of a, so there's a lot of things that are your intuition about thermodynamics. When you meet the real world, there's a lot of things where you find out, I thought I understood thermal, and now I don't. This is maybe one of them. But so another one is, it turns out that the CO2 contents that you get in for example, exhaust gases. So you would think, wouldn't you, that if I have a mixture of, say, 15% CO2 and 85% nitrogen, there ought to be some temperature or pressure where I can turn that CO2 into a liquid. Because everything can be turned into a liquid or a gas or solid at some pressure. you get mixtures, that's not necessarily the case. So in those mixtures, there is no pressure or temperature at which the CO2 in that mixture will be liquid. So you're going to be a solid or a gas. You can't turn it into liquid. So there's a lot of, the real world brings you a lot of thermodynamics that aren't so obvious. So the reason this is such a big issue, this is one of the important specifications for natural gas, is that if you pump the natural gas into a pipeline, pipelines go up and down over mountains, mountain ranges, and they go long distances. And so if you start off here, but you go up a mountain, and the pressure starts to drop because of the rise of the mountain, then you start condensing liquids. But this is a long pipeline, and I don't think Greg mentioned, and it might be 80 to 100 bar pressure, and it might be a couple hundred miles long. And so then you start this liquid forming in this pipeline, and the liquid, of course, is going to all run down to, it's going to start to pool in places. So if you go over the top or stay somewhere, it will start to pool in the bottom of this pipeline, and it will build up to the point where it's possible, and this happens, is that you can actually plug off the pipeline with this liquid, and then you start getting slugs of liquid going on your pipeline. And a slug of liquid coming to a processing plant that's expecting gas can do a lot of damage. And there probably isn't anything in our country that is as dangerous, potentially dangerous, as natural gas, as the interstate natural gas pipeline. So think about this. You've got, so the pipeline might be, some of them are many feet, typically they're 2 or 3 feet, but they might be as much as 5 feet in diameter. And they're 200 or 125 bar pressure, and they go for 125 miles. So if you were a terrorist, for example, and you found where one of those went through a major city and you blow it up, you've got 125 miles of 100 atmosphere gas that's combustible feeding this flame. So that is a very serious safety issue. And just like everything that stretches over hundreds of miles, it's almost impossible to constantly monitor what's going on these. There are gas lines that go under scout camps and places where people always need to be present. So for that reason, they put shut-off valves frequently in these pipelines so you can stop the gas flow if you have a major disruption or something else. But compressed gases, even if they're not combustible, are very, very dangerous things. And when they're combustible compressed gases, they're much more dangerous. Other questions?
Yeah, I was just gonna say, it would seem like it'd be pretty easy just to have a couple points in your pipe where you put a liquid collection spot. Do they do anything like that?
So they do have places where they collect liquids, but you know, if it's pooling up in one place, it's going to be coating the surface everywhere, and it's potentially corrosive. They make these little things, they call them pigs, that they send down the pipelines, and they're pretty cool actually. Some pipelines are big enough they actually have a place where a person could ride the pig go through the pipeline. So, basically it's just a little inspection device that sits in the pipeline, fills up about the entire pipeline, and just goes scuttling down the pipeline, taking pictures, see if the walls are cracking anywhere, if they're corrosive, if you've got places where things have been cooling. And they'll inspect the pipelines like that every couple of years or so, just for that reason. But they would much rather, and this is typical of industry, they just don't deal with liquids. So we're just never going to put anything in this pipeline that's going to form liquid. It's a way better solution than trying to go patch the problems when they occur.
So you hear a lot about oil pipelines and how the potential of them leaking and people like freaking out about that. Do people freak out about natural gas
They
pipelines?
should. They're way more dangerous. Well, the one thing about natural gas is when it does leak, it all goes up in the atmosphere.
Yeah, so it's not quite the
It doesn't-
environmental hazard
Right,
that
right.
people think of oil.
It's not the water hazard that oil is, for example. So, but it's a much bigger safety hazard, and just the potential energy that's stored in that gas is much higher than, if you get an oil leak, it's not going to blow. So 100 atmosphere pressure is, that would blow the quiet building to rubble, all right, if it erupted underneath us. And so 100 atmosphere liquid would be a relatively minor incident in the room in the quiet building. There's about, let's see, at 100 bar pressure, there's probably easily more than 1,000 times energy in the gas, just in terms of PV work that it will that's just a good thing to remember. So, other questions?
Well, I was just gonna say, how about some of those gas lines fail sometimes in the US?
Yeah, they do fail for reasons like we're talking about, some, or just structural reasons. I mean, everything fails at some point. But a normal failure, so a catastrophic failure like would happen in an explosion is hard to manage. Normally they will fail by some flange will start to leak and they'll be able to detect the leak and shut it down. Or they'll have something disrupt, something usually out of a pumping station that fails. So let's see, they call that retrograde condensation. So just something else to be, this would be great if you're going to work in the energy industry, you can use something like this. So the existence of this retrograde region is strongly dependent on the size of the molecule, not so much on the composition. So about 10% propane in methane produces a retrograde region that's about the same size as 0.06% heptane in methane. So a little bit of a big molecule will produce a big retrograde region. Relatively larger amount of a smaller molecule produces the same region. So just think it's not how much C2 and heavier you have so much as it is what the composition is. So here's some oil compositions and facilities. Here's one thing that Greg didn't even mention that we should talk about. So natural gas produces just slightly more than half of the CO2 per unit of electricity as a natural gas power plant as a coal-fired power plant. So from a global climate change standpoint, natural gas is a fairly significant improvement. But let me point out to you that most people, we talked about this, so most people say we want to manage. Turns out this number is completely arbitrary, but there's a goal that most of the world is set up to say we don't want the temperature of the Earth to change by more than 2 degrees. It's already changed by almost 1 degree. To get to the 2-degree goal, that's going to require a global reduction in CO2 emissions of about 60 to 70% compared to 2005 levels of production, which aren't that different than, a lot different. Well, in the U.S. they're not that different than they are now. Globally, they're higher now than they were then. So reducing CO2 emissions by 60 to 70%. So all of power generation combined, all of electrical power production accounts for about 33% of the total CO2. So we would have to reduce all of electrical power emissions to zero CO2 emission, or would be about halfway to where we would have to manage the temperature to 2 degrees. And so converting power plants from coal to natural gas is a move in the right direction, but it's not a solution to this problem. So the solution, and these large stationary sources of CO2 are going to be much easier to control than small distributed things like residences, and they're going to be much easier than mobile sources like automobiles and airplanes and things like that. So the real goal is, I think the real goal, if you're really serious about climate change, you got to find a way to get the CO2 emission to zero, not reduce it by 50%. Now, reducing it by 50% is like halfway to zero. But if in the process of reducing it to 50%, you've created something that's got a 60-year lifetime, which is about what we've done for natural gas combustor, then you might be doing more damage than good. For that reason, the EPA actually put limitations. So they passed, we'll talk about this later in the semester, but they passed some regulations about how much CO2 you can emit, and they limited the amount of reduction that you can get by changing to natural gas, because they don't want everybody to just switch to natural gas, and now they've got a harder problem that's now a 60-year problem to solve, because eventually you need to get down to pretty close to zero. But aside from the CO2 emissions from natural gas processing and natural gas power plants have another relatively large impact on climate change. So natural gas or methane remains in the atmosphere less time than CO2, about 12 versus 50 to 200 years for CO2. But it's way more potent. So when you average out its lifetime and how much radiation it absorbs, it turns out that 1 molecule of methane is 20 to 35 times as potent as one molecule of CO2 over the roughly 100-year lifetime that they might both be in the atmosphere for at least part of that lifetime. Just even a little bit of methane escape into the atmosphere has a big impact on climate change. And there are small leaks of natural gas that have large effects on climate change. The concentration in the atmosphere of H2O is on average about 0.5%. CO2 is about 400 parts per million now. And methane varies significantly from place to place. So a good rule of thumb for you to think about when you're working in an industry is that everything leaks to some extent, all right? There are no pumps, there are not even any pipe unions that don't leak. And so, especially when you have 100 bar pressure natural gas on one side of that leak and atmospheric pressure on the other. And so people have spent a lot of time trying to figure out how much natural gas is leaking into the atmosphere. And did it two major ways. One was they went to a bunch of operating natural gas facilities and actually measured the leaks in every location and calculated how much total natural gas was leaking into the atmosphere and how important that was. And came up with a relatively insignificant contribution to global climate change. But the only places that would let you come do that are places that are very well run, right? So how many people are going to invite the EPA on site to measure leaks from natural gas? Probably not the sloppy organizations where most of the leaks are coming from. So the second approach was to just go measure the methane content in the atmosphere and compare it where people are doing natural gas processing to where they're not. So you have a baseline in terms of the natural methane content and then the methane content where they're doing the processing. And they give up a much, much larger number in terms of the amount of methane that's getting into the atmosphere. And the second, and it seems like since then people have been redoing the studies, and it seems like the second study is more significant. So let me just talk briefly about the greenhouse effect and then we'll take a break. So this is the climate change, the essence of the climate change issue. When the sun shines at us, it has radiation flux as a function of wavelength that looks like this yellow bar here. On the Earth, and in this bar, there is essentially no absorption of radiation from CO2 or nitrogen or oxygen or methane, or almost anything in the atmosphere. If there was some absorption, then the skies would be colored because it would be selectively absorbing light at one region or another. But so the fact that just slightly outside of the visible region is water absorption here, and there's a lot of absorption into UV, which we're grateful for, because if there weren't, we would all be suffering from skin cancer way worse than we are. But in the visible region is from about here to about there, where our light sees. There's virtually no absorption in the atmosphere. There's scattering by particles, but there's no absorption in the atmosphere. But the Earth is pretty warm compared to space, so the Earth re-radiates this radiation back into space. But the Earth is cold compared to the sun, so this is the spectrum of the Earth's radiation. It's clear out in the infrared. Out here in the infrared, CO2 and water and methane and almost everything else, but not nitrogen and oxygen, absorbs moisture or absorb radiation. And so some of the radiation that the sun deposits on the Earth is trapped in the atmosphere in what we call the greenhouse gas effect. And we are very glad for that greenhouse gas effect, because if it were zero, the Earth would be much colder than it is now, so cold that the oceans would freeze over, and life as we know it on this planet wouldn't exist. Life forms would have to be very different. Even in the tropical regions, it would be way too cold for current life forms to exist. So the problem is, though, that we have increased the historical average concentration of CO2 in the atmosphere is about over the last several thousand years until the last few tens of years, is about 280 parts per million. We're now at 400 parts per million, and that increase is due almost entirely because of the combustion of fossil fuels and dumping CO2 into the atmosphere. And the increase from 280 parts per million to 400 parts per million is driving a temperature and a climate change that's the essence of what everybody's arguing about. So we'll talk in depth about climate change later, but But from the natural gas perspective, so these are these two studies that I mentioned about. So the EPA went around and measured leaks at specific places. They found out that about 1.35% of the natural gas leaks into the atmosphere at some point during its processing before it gets to whatever it's going to be at the end. NOAA, the National Oceanographic and Atmospheric Agency, which is another government agency, measured the CH4 in Utah, among other places, and they estimated leaks that were 10 to 20 times higher than what the EPA measured based on that. And so that at this level, the natural gas that leaks into the atmosphere during processing is a significant contributor to climate change. At this level, it's a relatively minor contributor compared to the CO2. So at 20 times higher than this number, the methane leakage from natural gas processing is as significant as the CO2 emissions from a power plant in terms of its impact on climate change.
But it only lasts 10th as long, so it seems like even if you leak a ton, the savings on CO2 would be tremendous.
So they factored that into these calculations as how long. So what they're really calculating is what is the contribution of methane to global climate change. And because these numbers are so far apart, you can get very different answers. But at the high end of these numbers, it's quite significant.
So you mentioned that like they have lifetimes. Does that mean like the CH4 decays into CO2 and like 4 waters or
Right.
something?
Right.
Two waters.
Right, and CO2 absorbs into plants or into the ocean or sometimes rocks. So they both find places in the environment where they go eventually. CO2 takes a lot longer.
You mentioned that we're going to talk about global warming more in the future, but my impression that it's a similar argument, but one measurement says it's really significant and it these two studies. One says it's super significant and others say that it's terribly insignificant.
So climate change has become highly politicized, unfortunately. So actually, we will go through this. We will look at what the scientists say, and what you will find out is that most of what you hear, even the climate change enthusiasts say, is not supported by data. That is, for example, the big drought that California is just coming through. That drought was not, the scientists will tell you that drought was not caused by climate change. It was worsened by climate change. The fact that because the climate is warmer, when they get into a drought, the soil gets drier than it would be if it weren't as warm outside. So in that sense, climate change contributes to the severity of consequences of the drought. But the drought itself, the fact that it didn't rain for several years in California, put them into the position they're in right now, was not driven by climate change. There are not more hurricanes now than there used to be that are being driven by climate change. And this is the United Nations IPP reports. You can read this in there. And they're saying there's no statistical evidence that the frequency or the intensity of hurricanes has increased. The drought in California was not caused by it now. You know, if you talk to Jerry Brown, whom I respect enormously, governor of California, says the climate is a change here. These are the adjustments we have to make. And California is very ambitiously reducing their CO2 emissions, much more ambitiously than the EPA is requiring of anybody else. On the other hand, almost all of the arguments against climate change are demonstrably wrong. There is no doubt that the temperature of the Earth on average is increasing, and some people argue, is this people that's causing it, or is it just a natural fluctuation? But we'll go through the data and you can make up your own mind, but you will be very hard pressed to find any credible scientist atmospheric scientist, climatologist that would argue that that climate change is not a human caused significant perturbation from where we've been in the past. And so on both sides there are extreme people who are citing data that aren't right. I hope when we finish this class you'll be able to know this is what the data actually say, this is what the reports actually say. More importantly, these are the solutions that we can live with, that make sense and are effective, not just knee-jerk reactions to something. And there's a lot of that. A lot of what people are proposing as solutions really don't help very much. Planting trees, for example, is not an effective way to affect CO2 emissions or concentrations in the atmosphere, for example. So let's take a short break and then we'll get back to talking about pollutants in general. Power generation system that it gets formed in the atmosphere, and ozone, it's up in the ozone layer at the very outer reaches of the atmosphere, is a very good thing that absorbs UV radiation and protects us from ultraviolet light. But ozone in the troposphere, where we live and where all other animals live, is a very unhealthy thing. So ozone is typically a summertime or high temperature problem in the atmosphere, and is a major consideration. And then finally lead. So lead is mostly been removed from products, and so we used to put lead in paint, we used to put lead in gasoline for reasons that we talked about, but we don't do either of those things anymore. So mostly this is old stuff that we're dealing with, but there are some very significant lead regulations in this Clean Air Act as well. So those are the pollutants that we worry about. There are some other ones that there are two of them, all of them are now regulated, but only very recently. So the regulations for CO2 emissions from power generation were passed last summer, a year ago this summer, and they came into effect about this time last year. They are being challenged in court, like everybody knew they would be. They've already been challenged in court, but I think everybody expects that some form of those regulations is going to get through the court battle, and we will be looking at CO2 regulations that are pretty severe, actually. So that they're going to cause major changes in the energy industry. Mercury passed 2 years ago, those regulations. So the mercury in the atmosphere is, we don't think of mercury as part of our atmosphere, but we're all breathing a little bit of mercury, and a little over, somewhere, depending on whose data you read, a significant fraction, a third to a half of the mercury in the atmosphere comes from combustion processes. So it's not the rest of it's naturally occurring mercury that would be hard to control. But, so mercury emissions from the power plants are now being regulated, and people are controlling mercury emissions. And ammonia is another major issue. Ammonia is a part of the most effective NOx control systems. Inject ammonia over a catalyst and react the anode and form N2. And some of that ammonia escapes into the atmosphere, and in regions that are very intensely agriculturally active, like Cache Valley in Utah, for example, ammonia from agricultural operations is also quite a significant emission in the atmosphere. It's, of all the things we've talked about, it's the only base in the atmosphere. The rest of them form acids, and its reaction with the other acids is a significant contributor to air quality issues in regions where it's emitted. So let's go through each one of those kind of individually and talk about what's important about them. So NOx. So the literature on NOx chemistry is enormous. I'm not sure what fraction, but it's quite a large fraction of the research that's been done in energy science has been done to figure out how to reduce NOx emissions from generation. So this is probably among the most complex and certainly one of the most important gases we consider talking about. It's primarily the pollutant in Wasatch Valley that's responsible for our air quality issues in the wintertime, which are severe. We have very, very poor air quality in some winters, most winters. So conceptually, there are three ways that you can form NOx. There's thermal NOx, which is most of the NOx that comes out of an automobile engine. And this is the high temperatures that are generated in the flame are high enough that you form some radicals, mostly OH and some oxygen radicals, and those radicals react with nitrogen, molecular nitrogen, and can form molecular reaction, nitrogen react for NO. And that's a process that we call thermal loss. It's driven by the high temperatures and by the radical concentrations. So nitrogen radicals are pretty rare because the nitrogen-nitrogen bond is very strong. So it's actually pretty hard to generate a nitrogen radical thermally. You can generate it chemically by reacting nitrogen with OH, or sometimes O, and then you'll chemically break the bond. To thermally break it is pretty hard. Prompt NOx is also part of what comes out of automobile engines. So that's NOx that is generated by hydrocarbon radicals, carbon or hydrocarbon radicals that are common in the very early stages of the combustion process. So when you start with a fuel, you start breaking it apart. So in your kinetics class, so some of these conceptual items maybe aren't so obvious. So every chemical reaction, essentially every chemical reaction is driven by radicals. Without radicals, virtually nothing reacts. And so radicals drive the chemistry, including actually the chemistry of your own body. So the radical generation of your body through chemical processes is what drives these. And so these unstable, almost impossible to measure, but clearly existent, quantitatively measured, clearly existent things that we call radicals are the backbone of all the chemistry that happens. So these two are things that happen with natural gas and gasoline and diesel fuels that have essentially no nitrogen in the fuel. Solid fuels like coal and biomass and black liquor and other things that come from solid processes also have nitrogen in the fuel. And when there's nitrogen in the fuel, the nitrogen in the fuel is usually a major contributor to NOx. And so they call that fuel NOx. And why is there nitrogen in the fuel? So how many of you fertilize your lawns? When you buy a fertilizer, there's 3 numbers on the bottom of it, right? So fertilizers are measured by their nitrogen, phosphorus, and potassium contents. And the numbers that you see at the bottom are how much nitrogen. So plants have to have nitrogen to live. You have to have nitrogen to live. So nitrogen is an essential component in amino acids, which are the building blocks of all of the proteins that go into any living thing. So nitrogen is an inherent part of anything that's alive. So you can't expect things to not have the nitrogen in them. They don't have large quantities of nitrogen. They're mostly made out of carbon, but there's significant and measurable amounts of nitrogen. And in the case of natural gas and petroleum, the nitrogen is more reactive than carbon, and so over long periods of time, they've reacted and gone into forming molecular nitrogen eventually into the atmosphere. But in the case of coal and biomass and black liquor, the nitrogen, a significant amount of nitrogen is still in the fuel, and it forms NOx. So it usually does so by going through a HCN intermediate step or an NHX intermediate step and eventually forming NO. So equilibrium NOx is, NOx is never in equilibrium, and so this is really detailed chemistry that is kinetically limited and very complex. Just about everything reacts with just about everything at some level. So the chemical mechanisms that describe the chemistry of NOx formation in a gas turbine, for example, involve over 300 elemental steps and 70 different compounds, 70 different reactive compounds. So it's a very complex network of chemistry. But equilibrium helps you understand, at least conceptually, some of what happens. So when we get to fuel temperatures, remember flame temperatures, adiabatic flame temperatures are over 2,000 degrees, and we have an equivalence ratio where everything over here means that we have more air and less fuel than we need, and everything over here is more fuel and less air. And here's where the air and fuel are exactly balanced, and recognize this is a logarithmic scale here. So at those high temperatures, you can produce in equilibrium large quantities of NO. So what happens in a flame is you start off typically with virtually no NO in the gas, and as all these radicals are reacting, the NO is trying to get to its equilibrium point at that high temperature up here. But then quite rapidly in all these combustion systems, the temperature drops, and more importantly, the radicals go away, and the chemistry stops, and the radicals go away. And so, with the chemistry stop, it freezes the NO concentration at close to something like here. Some small amount of it actually reacts and disappears again, but as you cool down, the NO concentration is kind of frozen at wherever it was in this chemical mixture as it was being generated. And so the amount of NO that comes out of the back end of an exhaust system is way super equilibrium. So way above its equilibrium values, not because it went above equilibrium, but because equilibrium changed because the temperature dropped, but it got stuck where it was, and because the radicals had all disappeared, and so the NOx stayed at a high level. So in your homework, you'll do a little bit of work with this so-called Zeldovich mechanism, or the modified Zeldovich mechanism. This is a very simplified mechanism to try to understand thermal NOx formation. So nitrogen can react with oxygen radicals to form NO, and a nitrogen radical which will react with oxygen to form NO, or nitrogen radical to react with OH to form NO, and a hydrogen radical. So those mechanisms, and then the modified portion of it is this last mechanism is, so if you start off with something like this, and this is common to most chemical mechanisms, is that frequently there's no place for the thing to get started. There's no source of radicals. That is, if we didn't have any hydrogen or oxygen or nitrogen radicals, then the rates of those three reactions would be zero, right? Because this would be zero, that would be zero, this would be zero, nothing's reacting. So there's got to be a source of radicals somewhere, and in the model, the source is that oxygen is dissociating to form oxygen radicals, and then that's what gets the rest of this chemistry going. So if you take those four reactions, and frequently this one will be assumed to be in equilibrium, you can kind of describe how NOx formation, if you knew the kinetic rate constants for each one of those, and in this equation, you can kind of understand how things form. So in your homework, one of the things you're going to do is, so just remember your normal chemistry, and if we're trying to, when we want to write the reaction rate expression in terms of things we can measure. And we can't measure nitrogen radical or oxygen radical or hydrogen radical concentrations. So how do we change this kinetics into something that we can measure? That was the whole objective of what we did in kinetics class with the steady state assumptions and things like that, is to try to eliminate the radical concentrations. So if you make the assumptions, so this is, write down the kinetic expression, assuming those are all elementary reactions for NO, for example, and it has all of these components, but it has things like nitrogen and oxygen radicals in it. And in order to figure out, we need to put something in there that's something we can measure. And we do that by writing down the expressions for each one of those radical concentrations, and then assuming that those are zero, and solving using those several expressions. You can solve for example, nitrogen radical in terms of things that you can measure, like NO and N2 and oxygen, and substitute them all back in there and come up with an expression that makes some sense. So this one's more complicated than the one you do in your homework. It's just 2 steps, and you do a balance around those radicals and come up with an expression that says NOx, the rate of NOx formation should be this in terms of an expression that doesn't have any radical concentrations in it, because we can't measure those radicals. So everybody comfortable with that? So these in the thermal Zeldovich mechanism, these are the parameters that go into those reactions. So prompt NOx is described by a similar reaction mechanism with radicals that are hydrocarbons. This is called the Fenimore mechanism. And fuel NOx just starts with fuel nitrogen. This is fuel bound into a very complex molecule like coal or biomass. As it just thermally dissociates, it forms things that we can identify like HCN or NHX, less frequently N or sometimes CN. And then these react competitively. They react with NO to form molecular nitrogen, and they react with oxygen to form NO. And then that NO reacts with these and forms molecular nitrogen. And people can spend a research lifetime looking at the formation of the NO through these mechanisms. This is a large part of many people's work in combustion systems. So SOx, by comparison, is much, much easier. So fuel-bound sulfur, pretty much quantitatively, not pretty much, does, well, I'll go back to it. Pretty much quantitatively reacts to SO2 in the atmosphere. If you know how much sulfur there's in the fuel, you pretty much know how much SO2 you're going to generate in the exhaust. And the only exception is that some ashes, particularly calcium-rich fly ashes, the inorganic portion of coals actually capture SO2 and convert the calcium to calcium sulfate. And so usually they'll take 80% of the sulfur in the fuel as a measure of how much sulfur is going to be emitted by the power plant, and you're done. So, you know, books and research articles on NOx would fill this whole building on SOx. You can put those on this desk, right? So it's much easier to understand. SOx removal occurs. I mentioned this, so SOx is overwhelmingly in the form of SO2 in the flue gas. Usually the SO3 contents are essentially immeasurable, but SO3 is actually the equilibrium form of sulfur. That's just to show that. By the time SO3 becomes the equilibrium favored form of sulfur, the radicals are all gone, and there's nothing to help SO2 react from SO3. And it doesn't, even though we write it this way, you might think of it this way, it doesn't just react with oxygen to form SO3. In the atmosphere, though, it does react to form SO3. So SOx removal is done typically by fuel processing. In the case of diesel, they remove the sulfur from the fuel before they put it in your tank. Or by reacting SO2 into flue gas. In the case of solid fuel combustion, they'll inject at the tail end of the combustion process, they'll inject a bunch of typically calcium and turn calcium oxide into calcium sulfate, which is that's usually done in a wet process. So they turn it into gypsum, which is the material we use in wallboards and construction. And you turn it into a relatively inert, benign compound that can either form into wallboards and sell as a construction compost or as landfill, or is stable and no longer reactive in that form. Sometimes, so SOx removal is frequently actually motivated by protecting catalysts. So SOx is a very common catalyst poison. That's the sulfur in general, and so frequently you'll remove sulfur because there's a catalyst somewhere in the process that can't stand the sulfur. And it reacts across NOx catalysts to form SO3, so even though it won't react by itself, the same catalysts that they use in power plants to reduce NO concentrations also promote SO2 to SO3. So part of the science of those catalysts is to try to get one of those reactions to occur and not the other. We're getting pretty good at that, actually, preventing the SO2 reaction.
So what do they do with the SO2 that's in the fly ash and they filter out?
So the SO2 that's in the fly ash, so the fly ash itself gets typically landfilled, or the best use of fly ash, and this happens with almost half of the fly ash in the United States right now, is you can actually replace cement. So this is where chemical engineers should become better civil engineers. Concrete is solid material that you walk on. That's what a sidewalk is made out of. Cement is a powder that goes into making concrete. But cement and water and gravel and sand and fly ash sometimes all get mixed together to make concrete. We use those terms interchangeably a lot, but they really mean different things. So, and fly ash can actually displace cement. You can use a lot of concretes are made with 20 or 30% fly ash instead of the concrete. And in the long term, the fly ash actually makes the concrete that you produce some better material than it would be without the fly ash in it. So there are other uses for it like that, and a lot of it gets used that way. Some of it just gets buried in landfills.
And the SO2 doesn't escape out of the...
No, so the SO2 in that case is in the form of calcium sulfate, which
Oh,
is,
okay.
you know, it's the same as the wallboard in your house. And it's stable and benign and not a health threat to anyone. So primary particulate matter, primary particles are the things that would come out as particles in the gas. And so this is, for example, some of the fly ash that escapes the fly ash capture systems will come out as primary particulate. The soot that comes out of diesel engines is an example of primary particulate. So these small particles that come out of most combustion systems are the primary particles, but we've gotten very good at eliminating them. And so most of the particulate that gets into the atmosphere, it used to be when you look at a stack and you see this big black plume coming up out of it, and all of the black, dark stuff is particulate. Now you look at most stacks and you see a big white plume coming out, And what you see is almost entirely moisture. So there are still pollutants in that stack, but you can't see them because they're not visible in visible light. What you see is mostly warm water that's condensing to form tiny water droplets, and the big white billowing stacks that you see are not pollution, they're just water. If it is dark, then it has a bunch of particulate in it. Diesel soot is the most recent thing to be regulated, so they now have active filters in diesel engines since 2008. I think they've been required to put these filters in engines. They filter out the soot, so there's way less soot being generated by diesel. Another, I don't have it up here, but another form of primary particulate in the atmosphere is actually they call road dust, which is a big component of which is your tires. So you ever wondered, where does all the rubber that used to be on my tire, where did it all go? And part of the answer is that just the friction tears off very tiny pieces of it, and it's floating around in the atmosphere, and that's part of what we're all breathing. So a lot of it ends up just on the road or in the ground around the roads. So soot and NOx and diesels are inversely correlated. So it turns out it's really easy to decrease the soot in the diesel if you don't care about the NOx, and vice versa. You can get the NOx really low if you don't care about the soot. Getting them both low is again, the subject of a lot of research. So secondary particulates are the ones that form in the atmosphere, and those are by far the most common right now. And those come from NOx and SOx. They react in the atmosphere to form typically sulfuric or nitric acid or other atmospheric compounds, and then those agglomerate into little droplets or sometimes solid particles that scatter light, and that's what, when you drive and look into Utah Valley or Salt Lake Valley in the wintertime, you see this kind of tan, gray haze that we're going in. That's most of the color that you see is associated with those compounds. And they're serious health threats, so they get it. So the reason that the small ones are so large particles in the atmosphere, your nose is designed to capture those. When you breathe air, the big particles are captured in your nasal cavities. And if you've ever been in a really dusty environment, you know your nose is evidence of that. But the small particles will just go with the gases down all the way into your lungs. And in your lungs, the particles are very, very small. And some of them deposit in your lungs. And that's the health effect, the main problem with the health effect. It doesn't, and the fact that they're acidic and they get into your lung makes biological damage even worse than it would be if they were just inert particles. They're bad as inert particles. They're worse when there's sulfuric acid or nitric acid that you're breathing. That health issue is big enough that we should consider this. That most of the physicians in Utah and Salt Lake County say that it is unhealthy for a pregnant woman to live in this area during winter time. So it's a pretty severe problem around here. So how do you control it? So the anthropogenic, that means man-caused, and the natural sources contribute to air quality issues. Some distributed sources include ammonia from bacterias, and home fireplaces are terrible. Don't ever burn anything in your fireplace other than natural gas. And road dust, which is mostly primary material. There are major episodic particulate releases associated with volcanoes. For example, natural release of a volcano erupts. A lot of particulates in the atmosphere, so much so that volcanic eruptions have caused worldwide crop failures in the past. That's happened several times in the past where there's actually been a lot of starvation. And that will go on for the effect of a major volcanic eruption on both the temperature and the climate of the Earth can go on for years. Some of those more famous ones are indicated here. So CO2 we already talked about, and we're out of time, so we'll finish this on next time. So I think you're pretty prepared for your homework, and just send me an email, and we'll just get things wrapped up. Have a good week.